So I'm going to talk about joint work with my colleague Gregor Kemper from the Technical University of Munich in Germany. And my talk is on reconstructing a room from echoes, but I want to look a little bit at the case where the data is noisy, so not such a pure math problem. But I will first start with the pure math problem. So what are we talking about? I'm talking about the case where we have a room and we're going to put some microphones inside the room and we're going to put a loudspeaker in the room, and the loudspeaker is going to make a little bing, and then the microphones are going to hear the bing, but it will also hear the echo of the bing on the wall, so that the sound comes from the loudspeaker, goes on the wall, and is acquired by a microphone. And let's see, I'm going to draw a little picture here. So we've got a wall. And what I mean by wall is just a planar surface, finite. So it doesn't need to, when I say we have walls, they don't need to touch one another. They don't need to be any particular arrangement. A ceiling would count as a wall. A floor would count as a wall. So this is my wall. And I have a microphone in some position. I also have a loudspeaker. Let me put it here. So this is going to be my loudspeaker L. Maybe draw a loudspeaker. This is a loudspeaker that makes a little bing, bing. So in position L. And so what it does is it takes the sound, the sound bounces on the wall and is going to come back and be heard by the microphone. Now, it turns out that instead of modeling the problem this way, we can think of the sound coming from what we call a mirror point. So if you take the loudspeaker position here and you do a mirror image with respect to the wall, say about right here, oops, here, then you can think of the sound as coming from that mirror point, and the time it took to go from here, can you see this, to the wall to the microphone is at the same time it took to go from that mirror point to the microphone. So when we talk about the wall, we often identify the wall with the mirror point, and we use the variable s to denote the mirror point. So, all right, so my microphone hears an echo. And that's the first order echo. Obviously, the echoes are going to bounce again on the walls and create second order echo, third order echoes, and so on. But we'll just focus on the first order echo. And the reason why we're interested in these first order echoes is that they give us the distance from the microphone to the wall. Well, we are going to try and reconstruct the position of S, the mirror point. And that mirror point, so we have a microphone, it hears a wall, and we're going to add more microphones into our rooms. So this one is going to be the first one, this one is going to be the second one, this one is going to be the third one. We're going to add 4 microphones because in order to do geometry, we're going to need 4 microphones. And each of these microphone is going to hear the same sound bouncing back on the wall. So this microphone, we will figure out how far it is from us. This microphone will figure out how far it is from us. This microphone will figure out how far it is from us by knowing that, because if you hear the echo, you see how much time it has elapsed between the original sound and the echo. So knowing how much time it took, you know the distance. So from the echoes from the wall, we're going to get distances. So we have our first microphone, M minus S, its distance squared to us is given by the time it takes for between the original sound and hearing back the echo. And then we add a bunch of different microphones, so then we get distances Mi minus S squared. These are going to be the distances between the microphone and the mirror point. I say distances, they're really distances squared, but we remove the square. There's always a square essentially, so when I say distances, I mean distances squared. And we have 4 of them. We have M1 minus S, M2 minus S, M3 minus S, and M4 minus S. So we have 4 distances for each wall because we have 4 microphones. So what happens when there are several walls in the room? So if I add a wall, say here, then I'm going to hear more echoes from my microphone. So then each microphone is going to hear 2 echoes, one from wall 1 and one from wall 2. If I add a third wall, one microphone will hear 3 echoes, one from wall 1, wall 2, and wall 3. So at the end of the day, I'm going to end up with a bunch of distances for each microphone. So let's say this is S1, this is my wall S2, and this is my wall S3. I'm going to have distances Mi minus Sj, I ranging from 1 to 4, and j ranging from 1 up to the number of walls. So I have a bunch of distances, and because they're echoes, I don't actually know which echo corresponds to which wall. I don't have a label to say, you know, this echo came from wall 1 or to wall 3, so I'm going to lose some of my labels. So in each microphone, here's a bunch of distances. These are unlabeled, but I know they go with the first microphone. So I end up with a bag of distances, a multi-set of unlabeled distances. We call that a bag of distances. So it's the multi-set of all the Dij's, j equal 1 up to the number of walls. And we have 1 for each microphone. We have 4 bags of distances. So the microphones can be somewhere in the room. They can also be put, in reality, we often put them on a moving vehicle like a drone flying around, trying to figure out its environment. And these are 2 different setups. I see there's a question, can you have second order echoes? Yes, you can have second order echoes. They are there. You need, when you actually do the signal processing to get first order echo, you need to filter them out to get to this formulation that I presented. But yes, the second order echo would give you more information and potentially would enable you to reconstruct even better. I don't know, I haven't looked into that question, but yes, second order echoes are interesting. They provide you with more distances. One could exploit them. I will only exploit the first order echoes in this talk. So I have a bunch of distances, a bag of distances for each microphone. I have 4 of them, and I would like to know where were the walls. I would like to reconstruct my environment. So that's a problem. It's a problem that comes up often in engineering. You're trying to map your environment. You'll take a little robot, you'll navigate, and you want to know where are the walls, where are the obstacles. So that's a problem of mapping. You can set up the problems in different ways. You can have 4 microphones in non-planar configurations. Or you could place those 4 microphones in non-planar configuration on the drone. And then the drone moves around. And you can also, if you want to, you could place the loudspeaker as well on the microphone. These are all potential experimental setup. And the question you want to answer is the following. If 4 microphones hear the echoes, type of a number of wall, and I don't know how many. And in fact, not every microphone needs to hear every wall. But I would like to know, can the walls be reconstructed? From the echoes. So that's my question. So I will first discuss the exact case before I talk about how to take this exact result and carry it over to.
Is the microphone configuration calibrated? Is it known?
So you can, know where they are with respect to one another fairly precisely. So that we'll assume is known. Yeah, makes the problem easier. But it's still hard even with that. All right, so what do I mean by reconstruct? I have to be a little bit careful here because we're not going to reconstruct exactly where the wall was. We won't know where it starts and where it stops. But what we will be able to know is we will be able to know the normal to the wall, and we'll be able to know 4 points on the wall. So we know the plane through the wall, but we know a bit more than that. We know 4 points that are on the wall. So, you know, if you do the convex hull of the points in the plane, you could figure out a piece of the wall, and then the wall might extend further than that. So that's what I mean by reconstruct. That's all you can do, really. So reconstruct is recover the mirror point, S for the first wall, the mirror point S for the second wall, and so on. You want the mirror points for each wall. And this will actually give you the normal to each wall. Because if your wall is here and your loudspeaker is here, I need to put it a little bit more below. If your loudspeaker is here, then your mirror point is going to be right there. So once you have the S from the loudspeaker position, you can find out the normal to the wall. And after that, you can also recover 4 points on the wall, because the microphone, say M1, is going to, half of the distance between M1 and S is on the wall. So this will give you 1 point on the wall. M2 will also give you 1 point on the wall, and so on. So you'll get 4 points on the wall with the 4 microphones. And that's really all you can reconstruct. So we cannot do magic here, but that's good enough. All right, so what do we know about reconstructing a set of points from unlabeled distances? I'm going to go back and talk about, you know, a previous result where you know, we start with from some points P1 up to P, say N, and some d-dimensional Euclidean space, and then we compute their pairwise distances. So it's often common, it's common to organize these square distances inside a matrix. So you put the distance from the first to the first to the second, the first to the third, the first to the fourth, and so on, the first to the last, and the first row of the matrix, and then you continue this way for the other entries of the matrix, and so on. So you have a nice matrix of square distances. So here Dij is the square distance between Pi and Pj. And we do know that if we have the labeling, we can of course reconstruct the point configuration from the matrix. We can go back up to a rotation, translation, and reflection of the point configuration. So this is mod n. But if we decide to drop all the labels of the distances, if I remove all the labels, then I end up with a huge bag of distances, a multi-set of numbers that correspond to my distances, and I don't know which number corresponds, which distance corresponds to which distances, but we do know that we can actually reconstruct the point configuration. The inverse is well posed, up to origin motion, of course, for generic point configuration. So yes, we can invert up to En for generic point configurations. So it doesn't work all the time. There are some exceptions, and I will show you an exception just because it's a fun example and I like to look at it. And it took us a while to find it. So one example is a little podium here. You can build, you can put 4 points in the plane. The top of the podium has distance 2, the bottom has distance 4. The sides √2 and √2, and then in between, naturally, you end up with a √10 here. So that's a point configuration. I'm going to take the same exact distances and I'm going to stick them inside a different shape, namely the kite. So here's the kite. We've got a √10 here, a √10. I need to put my √2 here and √2. Wow, I should have exchanged them. Like my drawing doesn't look so good because √10 is bigger than √2. Anyway, 2 and 4. You can check this matches 2 different shapes, completely different shapes. So these are not equivalent up to origin motion, but yeah, they have the same bag of distances. So there are exceptions, they're hard to find. There's an algebraic condition for checking for potentially for checking if a configuration is potentially one of these exceptional ones, but there's still a lot of work to be done to really understand what is the set, this exceptional set. And some people are working on that. So, but we know that there's a chance that we might be able to reconstruct a point configuration, even if we don't know all the labelings of our distances. And, you know, the situation we have is very similar, right? So what is similar about it? So we have some points that we know, right? The microphones. So M1, M2, M3, these are knowns. And then we have some points that we don't know. These are the wall points. And then we are mapping this to a set of distances. I'm going to first arrange the distances inside a matrix so we can see what distances we have in relationship to the previous problem. So if I put the M first, so M1, M2, M3, M4, and then I'm going to put the S's, S1, S2 up to Sn, and same thing on this axis, M4, S1 up to Sn. So first I have a block in the corner that gives me the distances between the microphones, and these I know. I can measure them fairly accurately, so I don't need to recover them. So I'm going to write them with big letter Ds to distinguish them from the ones that I don't know. So this block here is known. And then I'm measuring from my echoes, I'm getting the distance between the first microphone and the first wall, the distance between the first microphone and the second one, the distance between the first microphone and the end wall. And this will be put into a bag. I also get the distance between the second microphone and each of the wall, and 3, 1, 3, 2, 3, and finally the distance between the fourth microphone and each of the wall. So I get 4 columns of distances. And obviously this, you know, it's a symmetric matrix, so I don't need to worry about the bottom, but the thing is I don't get anything here. This is, I don't get any of these distances. I don't get any distance of the between the walls. And so I'm missing quite a bit of entries in that matrix. Now in terms of the relabeling, I take each row here and I put that into a bag. So this will give me a bag of distance between the first microphone and the walls. And then I take the second row and I also put that into a bag. I take the third row, I put that into a bag, and I take the fourth row and I put that into a bag. So I have 4 bags. So I have partial labeling, and the bags are separate into 4. So I know the first index, I just don't know the second index. And I also have this big block here that's known, but all of this is unknown. So it's similar. Yes, I see a question here. A counterexample when you have n bigger than d plus 2 vertices. I don't have that many counterexamples, and so the answer is probably no, but I would have to think about the specific dimensions that you're giving me there. Yeah, the examples are hard to find. I think I could give you names of people who are actually looking at those, and they have maybe they have found some more. All right, but in this case, it's harder and it's easier. It's harder because we're missing entries. But it's also easier because we have a partial labeling. So can we also, solve this problem? Can we reconstruct, go this way?
Can I quickly ask a question? So the small D's, are they known or no? So you said the capital D's are known.
They're measured. They're measured, you know their values, but you do not know their label.
Okay, thank you.
So these are known up to a labeling. And these are also known up to labeling, but the labeling question is within each set, like it's within each row. So you know which row they belong to. So that's where we're at. So we, is the inverse map well defined? Obviously up to rigid motion because there's no way to reconstruct the position from distances. So in the exact case, we have an algorithm that actually reconstructs the wall positions. And also we have a theorem that guarantees that the reconstruction is correct and unique in generic cases. And the genericity is Well, if you assume that the walls are in generic position, that's a trivial result. But like nobody is interested in generic walls, right? Because walls tend to be, you know, in very special configurations. So we need to have a result that applies to all wall configuration. But the result shows that if either the microphones are placed in a generic position, non-planar, or if they're on a drone and the drone position, you know, like where it is in its orientation, if that is generic, then yes, the inverse is well defined. So there are exceptions. There are for given wall arrangement, there are certain positions of the drone that must be avoided, but these lie on the measure zero set. These lie on the zero set of a polynomial, so they're very, very rare. So what does the algorithm do? It proceeds in 2 steps. So the reconstruction method has step 1. The step 1 is sorting the echoes. It's figuring out the labels of the echo. So we call that echo sorting. And we do it with 4 distances at a time. So we pick a distance from the bag of distance of the first microphone. We pick a distance, let's call it D2, from the bag of distances for the second microphone. And we pick one from the set of distances from the third microphone, and one from the last bag of distance, the one for the fourth microphone. So we have 4 distances, and we're going to try to figure out if these 4 distances come from the same wall. So DI is the squared norms of MI minus some wall, let's call it SI squared, right? And we want to determine if the walls for each distance are the same. Is S1 equal to S2 equal to S3 equal to S4? So this can actually be done by looking at the matrix. 0, and then I'm going to put on the first row 0, and then I'm going to put my 4 distances, and I'm going to put a 1. It's going to be a symmetric matrix, so flip that a little bit. In the middle, I will put the distances between my microphones, and then I get this nice little block of 4, D4, 1, D4, 4. So this is my microphone block here. And these are 1s, 3, 4, 1, 2, 3, 4, and this is a 0. Now you might recognize the Cayley-Menger matrix, which has a determinant. So if the determinant of that matrix is equal to 0, then I know that the wall, that the walls are the same. So it's just viewing the wall points 1, 2, 3, 4 along with the microphone as a 5 simplex, and building a Cayley-Menger determinant for that 5 simplex and checking the vanishing condition. So if my determinant vanishes, I know that my point, my points are the same, my wall points are the same, and then I can reconstruct this point. So step 2 of my algorithm is to reconstruct. So in step 1, I know they come from the same wall, I want to reconstruct. So I have DI is MI minus now, let me call the wall point S. Right, so what does that mean? This is the norm of MI squared minus 2S dot MI plus the norm of S squared. So if I, and I have 4 of these equations, if I write them in matrix form, let's see, I'm going to bring this one to the left. It's going to give me D1 minus the norm of M1 is minus 2M1 and then the 1 times S and then minus the norm of S squared. And same thing with the second coordinate, D2 minus the norm of M2, I forgot the squared, is minus 2M2 and 1. D3 minus the norm of M3 squared, D4 minus the norm of M4 squared, minus 2D 2m3, 1 minus 2m4, 1. So this is the equation that relates the distances to the walls using the microphone position. If we call this matrix M and invert it, this tells me that, right, I'm going to put the 2 here, I'm sorry. Just looks better this way. Yeah, so now 2s and its norm are given by the inverse of m times these distances. This is how you reconstruct once you know that the distances fit. I just need to know if my D1, D2, D4 come from the same wall, and if they do, then I go ahead and reconstruct. And 4, this should have been a 3. All right. So that's how you reconstruct, nothing tricky there, as long as you know that they go together. So does this always work? No, not all the time. There are cases where a microphone arrangement might feel like it's hearing a wall, but it's really hearing different walls. So we call that a ghost wall. So I'm not going to draw an exactly counter example, but you know, something kind of like this, where you have your 4 microphones and there's 4 walls. Microphone 1 is hearing this wall. And then the second wall is heard by microphone 2. Microphone 3 is hearing a 3rd wall, and microphone 4 is hearing a 4th wall. This is my D1, my D2, my D3, and my D4. It's possible that these distances actually satisfy my sorting criterion. And then I'm going to think, yes, there's a single wall that gave rise to these distances, and I'm going to see a ghost wall. What's a good color for ghost? I guess purple. This is my ghost. So you take the same exact distances, and then you end up thinking that they came from here. That happens, but it's very rare. The theorem states that there's no ghost if the 4 microphones are in generic position, or if they're in a non-planar position on a drone, and that drone is in a generic position, you know, location and orientation in the air. So these are very, very rare examples, and you can get out of them by moving your drone just a little bit. So we know that works, and I see the time is yeah, almost up. So how do we add noise to that, right? Like, how do we deal with the noisy case? So in the noisy case, we have a problem because you know, we're checking algebraic condition. We're checking a 0 determinant, and that 0 determinant is, you know, going to be approximately satisfied when you add a little bit of noise to your distances. And the thing is that those ghost wall positions, they create an issue numerically. It's not obvious, and I've seen a lot of engineers who just go and solve the problem as if there was no issue, but near ghost walls, what you end up having, let me actually write it down. I know time is up, but I need to write and make this point. So when S1 is S2 is S3 is S4, when you have, when you're looking at the, you know, one wall, then yes, the determinant of your Killian-Menger determinant is going to be approximately 0, right? If you add a little bit of noise to each of your distances. But when they're not all equal, but you're near a ghost wall, so that's when they're distinct, but near a ghost, the determinant is also going to be close to 0, right? Because the ghost wall makes the determinant equal to 0. So you don't know how to distinguish those two. How do you know that you have a perturbation of a 0 number versus a perturbation of a small number that is close to 0, right? It turns out, I mean, you can actually study this problem by looking at using statistics if you have the right framework. A determinant is not going to help you solve that problem, but if you have a, if you measure your distances, right, like, so the idea is going to be you take your loudspeaker and you have your loudspeaker emit several beeps, beep, 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 several of them, so that you can do several measurements with each microphone. So then instead of having just one distance, you have several. So you add a little bit of noise to the distance, right? Every single time. So epsilon represent my noise. It's a random variable following some distribution. Now we could specify later. So then your DIK squared is measured as an approximate number, which is equal to the true value squared times the value of the distance plus some noise. All right, so this here is a random sample. A perturbation of the distance that you should be looking at, but you can't because you don't have access to the true data. So what you can do with these distance samples, you can do a sequence of reconstruction. You reconstruct your, what we want. Remember, we reconstruct this way. Right. But this time you have noise. So instead of having your DI here, you're going to put your noisy D1 and your noisy D4, and you're going to do this several times. So for every K, you're going to end up not with a reconstruction, but rather a reconstruction vector VK, which is a sample and observation of what you would want to get. So understanding the relationship between the samples and the truth is going to give you the answer to whether or not these distances correspond to the same wall. So if you to put it very simply, in a generic case, you have samples VK, which I will write as V1K, V2K, V3K, and then V4K. And you see from this representation here that the first three indices should be the point, the wall position, and this should be the norm of the wall position. So if I write my sample VK like this, this is a perturbation of 2S and then the norm of S minus the norm of S squared. In particular, if I take my V4K, this should be a perturbation of of my S1 plus S2 plus S3 squared plus 4 times S4, if you think of that as the fourth direction. So by you reconstruct, you get 4 entries, and there's an algebraic relationship between these entries. That algebraic relationship, you can see what it looks like for each of your samples. So you get samples of the value of an evaluated algebraic relationship, and then you can use statistical tools to say, from those samples, do I think I have a perturbation of 0, or do I think I have a perturbation of a small number? So using central limit theorem, laws of large number, you can make some conclusions about what you're observing. Am I going to converge to 0? Am I going to converge to something small? How many samples do I need to get a good estimate, and so on? So it's not really possible to play just with the Cayley-Menger determinant to actually see what's going on after the noise, but we figure out a way to do this by essentially doing the reconstruction at the same time as the sorting together. So I know this is very fast and not enough details, but hopefully I get a little bit of I give a little bit of an idea of how to take this exact theory and move on. And I'm happy to discuss more during the breaks or during the 4 minutes before the other talk. I don't know.
Thank you very much, Mimi, for this excellent talk. We have time for let's say 1 or 2 quick questions. Does anyone have questions?
Sure. Can I ask one?
Yes.
So do you have to sort of impose some noise model at the outset?
So you will, but you don't need to know too much about your noise depending on how you do it. So you definitely, the computations are crazy if you don't have zero mean noise. And I've been adding zero skewness. So with zero mean and zero skewness, third order moment, I've been able to actually get a pretty good statistical model and be able to make some conclusions actually and build like a hypothesis testing framework. So without too much, because in statistics, you have these great limit theorems like Chebyshev. So really to make, a hypothesis testing, sometimes you can get away with just the first and second order moment of a distribution.
So the idea is it adaptive? That is, the closer you are to a singularity, it will decide, it will realize that you need to take
Yes.
more
Yeah.
samples.
So with one sample, it's very easy to tell. It's very hard to tell because you don't have much information. You can do a statistical test. How far am I from the expected value? I have this set of samples that come from a distribution, and from the samples, you can estimate the distribution if you want, but you want to say, how close am I to a distribution that's the one that I would have if it was true? This zero, it's not actually zero mean, so I don't want to say zero mean. So one sample gives you a little bit of an idea, but as you keep adding samples, you can say, well, what's the likelihood that I observe these samples, given that I have this hypothesis of a zero Cayley-Menger determinant? And as you add more and more samples, whether your statistical hypothesis is satisfied becomes more and more clear. So if you have an infinite number of samples, you would know for sure. Now, well, the expected value of the average of your samples is going to be satisfying an algebraic condition that you can measure approximately. Does that make sense?
Right, but you can never tell, right? I mean, you can never tell how close, because you don't know how close you are to a singularity.
You can only tell, this is true, like you can only reject a hypothesis with a certain probability. You say, if my hypothesis is true, if this is a zero determinant, then the following probability distribution holds for this quantity. So then if you're in a spot that has only a 2% chance of being hit, then you can say, I can reject my hypothesis with a 2% confidence level. That's all you can do. But you can make that confidence level as small as you want.